Hello everyone, welcome to EEE 426 Biomedical Signals Instrumentation and Measurement Laboratory Final Project Demonstration. The title of our project is Multiclass Breast Cancer Classification Using Convolutional Neural Network. I'm Ishani Chaudhary, 1606131 from Group 7, along with my peers Asaduzzaman 1606165, Partha Bhumik 1606178, Asmia Hassan 1606191 and Muhammad Sadiq Yasir Toki 1606194. While cancer is one of the leading diseases cause of death worldwide today, in particular, the breast cancer death rate is very high when compared to other types of cancer. Its death rate is almost 8.2 million worldwide, according to World Health Organization. Most authors have focused on the field of automated two classes classification of BC histopathology image analysis, benign or malignant, with computer-supported diagnosis. We see that the above classification works are not enough effective to determine detailed breast cancer for giving treatment solutions. We propose to classify and recognize specific 8 breast cancer subclasses in 2 benign and malignant classes with the same brackets dataset using convolutional neural network, a special type of deep learning. Well, each class has 4 subclasses. The 4 subclasses of benign cancers are adenosis, fibroadenoma, tubular adenoma, and Pilot's tumor. The 4 subclasses of malignant cancer are ductal carcinoma, lobular carcinoma, mucinous carcinoma, and papillary carcinoma. Moving on to the next.
Now we will look over into the database. The breast cancer histopathological image classification is composed of 9,109 microscopic images of breast tumor tissue collected from 82 patients, and it contains 2,480 benign and 5,429 malignant samples of 700 by 460 pixels, 3-channel RGB, and 8-bit depth in each channel in PNG format. The dataset bracket is divided into two main groups, benign tumors and malignant tumors. Normally, benign tumors are comparatively innocent, presents slow growing and remains localized. On the other hand, malignant tumor is a synonym for cancer. Lesion can invade and destroy adjacent structures and spread to distant sites to cause death. Both breast tumors, benign and malignant, can be sorted into different types based on the way the tumoral cells look under the microscope. Various types or subtypes of breast tumors can have different prognosis and treatment implications. And we are seeing that the benign tumor has 4 subtypes, and also the malignant tumor has 4 subtypes. And here we are seeing a slide of breast malignant tumor. In current version, samples present in dataset were collected by SOB method. This type of procedure, compared to any methods of needle biopsy, removes the larger size of tissue sample and is done in a hospital with general anesthetic. We have seen that our dataset is imbalanced because the numbers of images in all the subtypes were not equal. So we needed to resample our dataset for better accuracy.
This is our proposed methodology. We first took the input images and split them into training and validation sets. The images were resampled to ensure an even number of samples in each class. The images were then augmented, and finally we created our CNN model using the Keras library and trained it. We split our dataset into training and validation sets using a 90-10% split. Because of the large class imbalance in this dataset, we had to downsample the 5th class and upsample the rest. We did this by randomly copying or removing images in each class as required. Finally, we ended up with a new dataset with 1800 images in each class in the training set and 200 images in the validation set. Because of the large amount of resampling, we had to heavily augment the images to increase the diversity of the training set. We performed image augmentation using the image data generator class in Keras. The augmentations used are shown in this slide. We used random rotations, vertical and horizontal shifting, brightness level shifting, shear transformations, and vertical and horizontal flips. We also rescaled the images by 1 by 255 to keep the pixel values between 0 and 1.
Now I am going to talk about the model we created to train and test the resamples Breakis dataset. We have 6 convolutional layers and 2 fully connected layers. We have used batch normalization in each and every one of them. The input images are resized to 256 by 256 with 3 color channels and fed to the first conv layer that consists of 64 filters, where the second layer has 128. Initially, our model was overfitting too much, and to fight this, we added dropout on layer 3 and layer 5 after the max pooling operation. Lastly, we used two dense layers, where one is the output layer used to classify 8 different classes of cancer. Due to multiclass classification, we used softmax as the activation function here, but the other layers have relu as their activation function. Training, we tried SGD, ADAM, and RMSprop as optimizers, but ADAM showed better results. With a very low learning rate and using categorical cross-entropy as the loss function, we achieved better performance from our model. We fought the adverse effect of imbalanced dataset on accuracy by using class weights in the model.fit function, where we prioritize the classes with fewer image sets. The training was conducted up to 40 epochs in Google Colab with a batch size of 32. The results will be shown to you shortly by my other partner.
Here is our final result. We can see that our model has maximum training accuracy of 93.83% and maximum validation accuracy of 88.75%. From the confusion matrix, it is clear that our model has a higher percentage of correct prediction for every 8 subclasses. Here we can see that we have a better learning curve than baseline model. We are dealing with highly imbalanced Bayes dataset, and from the beginning, we faced a lot of setbacks in improving the validation accuracy. After trying various techniques and lots of trial and errors, we reached our goal. Whenever we got stuck, the suggestions of our course teachers helped us a lot. In the future, we will explore different classification methods and the optimization of our parameters in our model. Moreover, methods to select areas with a lot of features to improve accuracy can be researched. Thank you.